Hello. We are at we're doing a stream number 2. Um, yeah, I want to learn variational inference, and also my my mouth is getting more and more busted. Um, the reason I think I need to understand this variational inference, and I really want to learn it, like why I'm spending the time learning it, right, is that I end up seeing a lot of this in literature, like a lot of generative modeling, builds on these foundational topics of Bayesian inference, like decision trees and all of that, for example, are not as like used, or I haven't seen it, but especially variational inference and VAEs and GANs. It seems like it's a pretty important topic, and I have taken a basic statistics course, and also I saw my friend Stefan, um, you know, write these blogs, and I want to really make sure I understand what the hell he's writing, right? Like, if I can't even understand this, then I would say I'm pretty pathetic, right? And so, um, so where do we even start? I think like for example, elbow and like what is variational inference all about? Like, I don't even fully understand that, right? So we were going over the derivation, right? And the derivation is better like expressed here. So what is the goal of variational inference? I don't even know, actually. Alright, so generally in maximum likelihood estimation, we want to find parameters that fit the data really well, right? And that's kind of hard, and so we can break down this probability distribution over some latent space, right? And so we can make a few assumptions. So this can be written as Q of Z dz times P. Like, this is just joint probability, right? Like, because I think of it as like, if yeah, I'm being stupid. Good. You know. Right. So, where were we in terms of alpha? Okay. We're going to variational inference. Okay. Let's make sure we write this down. Like we'll do the derivation by hand, and then we'll also make sure to write it in our notes. Okay. So, our goal in max MLE likelihood estimation is to find a set of parameters that maximizes. Oh my god, what am I doing? P of x. Like theta. Okay. Yeah, one piece of notation I saw in the other paper is like P of x theta versus, in which case they treat, in this case they treat theta as a random variable. And I don't really know the difference. Oh, so this is a typo actually. And in which case we're describing the likelihood function, right? Yeah, so we're trying to find a function that maximizes this probability function, right? So usually, you know, we work with like say Gaussian distributions, right? So P of x theta in this case, theta is parameterized by mu and sigma, and it's equal to 1 over 2. Do we know the Gaussian distribution? I should write down the Gaussian distribution from time to time over sigma square root of 2 pi. Known as 1 over 2 x minus mu over sigma. Yeah. Great. So that's your function. You plug in your sigma and your mu, and then your x is here. And then you get some number, and you want to find the number that maximizes this probability function, right? So this number is going to be maximized when it is equal to, if mu is 0, then you want x to be 0, and then so this whole number will be equal to 1, and then it's 1 over square root of 2 pi times sigma. Yeah. Okay. Right. And so that's our goal, right? But what they're saying is that finding this probability function it is hard to solve directly. Is that what they're saying here too? Right. Okay. Because in the Gaussian place it's pretty clear, but this might be some more complex function that we're fitting x to, right? For example, it could be a mixture of Gaussians, right? So you can imagine the data distribution that you're sampling from actually looks like this, right? A complicated function that you're trying to model. And if you do maximum likelihood estimation, what you're going to end up with, and I think ChatGPT explained this better to me, is, yeah, I guess I need to explain it myself, right? Because this is going to be equal to, yeah, it's like no n1 yeah, let's say there's 3 Gaussians, right? So you're sort of like combining the probability distributions of these 3. You actually don't know, right? Maybe you assume these 3 are like equal chance. And then when you take the maximum log, when you do likelihood estimation, it's very difficult to work with. Why is it difficult? Like in the traditional case, and that's actually what they do with expectation maximization, is that what it's called? So EM is actually, we'll look at these 3 and it's like, what's the probability of these parameters given my x? Hold up. Yeah, not my x like that, but like my x. And, oh, I should also record. Should be recording. Dude, my mouth really hurts, man. Like, look at me. It's because I got a wisdom teeth removal yesterday. Is it yesterday? Yeah. Oh, yeah. It was yesterday. Oh man, it's like absolutely painful. Can't barely talk. Okay. Anyways, in expectation maximization, what we're going to do is like we have these 3 different, and we're like saying, what is the probability of each of these? And then what are you gonna do? Yeah, I watched that video like today, and it was like quite helpful. But the actual algo is not clear. So we compute this number, and then how do we refit the Gaussians? Is this in low power mode? I don't want a freaking low power mode. Oh, there's a follow-up video. Okay.
we've got a bunch of data points, and in this case, converges. So we'll talk about mixture models and the expectation maximization algorithm. One way to think of EM, one way to let's look at an example in 1D. So we start with a bunch of points, one-dimensional points. We don't have any labels for them.
Yeah, let's go through an example.
So we'll talk about...
Do you guys... Okay, it's clear. I watched that 5-minute video, but...
for them. So the only thing we know is that they came from two Gaussians, and we want to discover what these two Gaussians are automagically. The way we're going to do that is we're going to start by placing two Gaussians in a random, in random positions on the line, and these are one-dimensional Gaussians, so their mean is just a number. So here's the mean for the yellow, so here's the mean for the blue, and they have the same variance in this case.
And we can compute.
So the first step of the algorithm, we're going to figure out how likely is each of the points to come from the yellow or from the blue. So basically, for each one of these points, we're asking a question. Use Gaussian, square it, divide by the variance, exponentiate, normalize. That gives you the probability that that point xi came from the blue Gaussian. Right? Probability kind of start to happen. So this will have a small number for blue, but the number for yellow is going to be much, much smaller, orders of magnitude smaller. So then, when you compute the Bayesian posterior, you take both of those probabilities from the blue and from the yellow, you combine them with the priors, by the way, assume priors are equal for now, stick them in the Bayes rule, BI for that point is going to come out to be almost 1. That point doesn't look like a sample from the blue, it doesn't look like a sample from the yellow, but it's much more, it's much more unlike the yellow than it is unlike the blue. So the posterior is actually going to be really high for that point. It's going to be assigned to the blue. And that's just BI for one point, and of course you would repeat it for all of them. Right? So for example, this point, would you expect BI to be high or low?
What is it?
Will it have a high probability PXI going to be? No, it's going to be very, very small, because that point is very far from the blue mean, and the blue variance is kind of spiky. It's not very spread out. Right? Will it have a high number for the yellow? It'll be even smaller. Right? And that's where interesting things start to happen. So this will have a small number for blue, but the number for yellow is going to be much, much smaller, orders of magnitude smaller. So then, when you compute the Bayesian posterior, you take both of those probabilities from the blue and from the yellow, you combine them with the priors, by the way, assume priors are equal for now. Stick them in the Bayes rule, BI for that point is going to come out to be almost 1. That point doesn't look like a sample from the blue, it doesn't look like a sample from the yellow, but it's much more, it's much more unlike the yellow than it is unlike the blue. So the posterior is actually going to be really high for that point. It's going to be assigned to the blue. And that's just BI for one point, and of course you would repeat it for all of them. Right? So for example, this point, would you expect BI to be high or low? It's the probability that that point came from the blue.
How do we use these numbers?
Well, no, actually, it should be pretty low, right? So this is very, very close to the yellow mean, and it's a lot further away from the blue mean. Right? So that point is going to be mostly yellow with a little bit of a probability for the blue. This one is going to be mostly blue with maybe a tiny bit of the yellow, and all of these are going to be blue pretty much throughout. So you compute the BIs, you compute the AIs, which are just 1 minus BI, so that's the probability that they came from the yellow. And then these numbers, the BIs, they basically represent the coloring of the points. Again, it's just like k-means, only in k-means, points would be either colored fully blue or fully yellow, and here we have sort of fractional colorings, right? This one is mostly yellow, this one is mostly blue, these ones are pretty much entirely blue, but you have a bit of a mixture, right? So the point belongs to both the yellow and the blue.
I'm saying P of theta 2. Yeah, that makes sense.
Distributions. And once I've done the coloring, I can do re-estimation, right? I can now take these colors and say, well, these points, they came from the blue, so now I can estimate the blue mean and the blue variance, because now I've got the assignments, right? And the way you do that is really simple. You just add up the x's for the points and you divide by the sum. Now, this sum is a little bit odd, and the first time you see it, it's going to look a little bit confusing. So what you're doing is you're taking each x value, x1, x2, and so on, you're multiplying it by bi, which is the posterior, and you're adding them.
And the new mean is simply the average of those values, but unlike this would be just k-means, right? If you just took these values and reassigned a centroid, but we're actually weighing these values by some weight.
Them up. Now, if you're having a hard time understanding what you're doing here, pretend for a moment that you're doing k-means instead of EM. If you were doing k-means, these BIs would be 0 or 1. The point either goes into the blue cluster or it goes into the yellow cluster. So 0 or 1. That you're doing k-means instead of EM. If you were doing k-means, these BIs would be 0 or 1. The point either goes into the blue cluster or it goes into the yellow cluster. So BI is 1 if the point goes into the blue cluster, and it's 0 if it goes into the yellow. Right? So if that happens, suppose that that point BI was 0, and for everything else BI was 1. Right? So what does that look like now? B1 is into the yellow cluster. You're multiplying it by BI, which is the posterior, and you're adding them up. Now, if you're having a hard time understanding what you're doing here, pretend for a moment that you're doing k-means instead of EM. If you were doing k-means, these BIs would be 0 or 1. The point either goes into the blue cluster or it goes into the yellow cluster. So BI is 1 if the point goes into blue cluster, and it's 0 if it goes into the yellow. Right? So if that happens, suppose that that point BI was 0, and for everything else BI was 1. Right? So what does that look like now? B1 is 0, so x1 is not a part of this sum, and b1 is not a part of the bottom either. Now what's left? b2 would be 1, b3 would be 1, all of them would be 1. So what you're doing is you're taking all the points except the first point and adding up their x values and dividing by the number of the points that went to the blue cluster. That's just n minus 1 in this case. Right? So your estimation is the same as if somebody came in and told you these are the points from the blue cluster. Right? Does this make sense? This is actually the critical thing. If you get this, you'll get the rest of it. This is good. Is everyone good on this? Okay. So that's how you re-estimate the blue mean. The difference now is BIs are not one-dimensional basal, so that's a generative smaller. It's a probability.
Did I miss some notation that I'm like fucking stupid about?
Clustering. It doesn't assign a point.
Oh
it says here's the
fuck
probability
off,
that it came
man.
from this distribution, and here's the probability that it came from that distribution. Okay. Now, once it has computed these assignments, the probability that it came from the blue, it's going to use those numbers to re-estimate the means and the variances to fit the point assignments a little bit better. So that part is very much like k-means. The part that's different,
What
figure out
is
with these
AI?
current to happen. Probability for the blue. This one is going to be mostly blue with maybe a tiny bit of the yellow, and all of these are going to be blue pretty much throughout. So you compute the BIs, you compute the AIs, which are just 1 minus BI, so that's the probability that they came from the yellow. And then these numbers, the BIs, they basically represent the coloring of the points. Again, it's just like V pretty much throughout. So you compute the BIs, you compute the AIs, which are just 1 minus BIs, so that's the probability that they came from the yellow. And then these numbers, the BIs, they basically represent the coloring of the points. Again, it's just like k-means, only and the now, this sum is a little bit odd, and the first time you see it, Now, if you're having a hard time understanding, if you were doing k-means, these BIs would be 0 or 1. So BI is 1 if the point goes into blue cluster, and it's 0 if it goes into the yellow. Right? So if that happens, suppose that that point BI was 0, and for everything else BI was 1. Right? So what does that look like now?
Like, what are
B1
you're
is 0,
anything,
so x1 is not a part of this sum. And B1 is not a part of the bottom either. Now what's left? B2 would be 1, B3 wouldn't be 1, all of them would be 1. So what you're doing is you're taking all the points except the first point and adding up their x values and dividing by the number of the points that went to the blue cluster. That's just n minus 1 in this case. Right? So your estimation is the same as if somebody came in and told you these are the points from the blue cluster. Right? Does this make sense? This is actually the critical thing. If you get this, you'll get the rest of it.
Oh, this is just notation. BI is just P of B. This is just the posterior problem. The likelihood function, and then what's the that's just your posterior. Just the oh my eyes. Yeah. After seeing the data, what is it that you think? Right? So you essentially just take these, instead of just taking these values and saying like, these xi's, like, we're gonna multiply by VIs. I think this is the most fundamental equation, right? And you divide it by
This is good. Is everyone good on this?
I understand.
Okay.
The AI, yeah. What's the point of AI?
So that's how you re-estimate the blue mean. The difference now is BIs are not just 0 and 1, they're probabilities, they're numbers between 0 and 1. So what it means is when you're computing the blue mean, these points, xn minus 1, they get the full weight, they give their full weight to the blue mean, and the point x1 gives a tiny fraction of its weight to the blue mean, and it's going to give a bigger fraction of its weight to the yellow mean. So that's the soft assignments for you. It basically, in k-means, a point contributes either to one centroid or to another. In EM, a point gives a little bit of its mass to every centroid, but it gives more mass to the centroids that it's more associated with. So that's what those BIs represent. And of course, you compute the variance in the same way. You take the deviations from this mean that you've computed. And again, this is not mu1. I'm sorry about the bug on the slide. This should be the mu of b, and this should be the mu of b as well. For the that the mean goes is associated with a yellow distribution. And you do the same thing for the mean. So when you do that, that is going to be the likely result. So your yellow Gaussian at one point is now all of these and the variance and those kind of stuff. So that's essentially how you estimate the means and the variances starting from nothing, just a set of data points. I only estimated the parameters of the Gaussians. I didn't estimate the priors. I kept the priors uniform. But you can also estimate the priors. So the way you would do that is the prior for the blue, you just add up all of the BIs and divide them by the number of data. Data points that you have, and that is the estimate for how basically what this is telling you is it's telling you what proportion of the points is the blue distribution describing now. What proportion of the data.
looks like the marginal probability.
Is it describing? If you do that, you actually have to be careful because a lot of the time, in a case like that, after the first iteration, blue would grab everything, right? And then yellow might get zeroed out. So that happens commonly. So sometimes you just peg the priors at equal at a uniform distribution. So you force them to be 0.5 and you don't re-estimate them. Okay, so they come from K. That's the weight, right? All of the estimation is based on posteriors, and the way you compute is not. That are not aligned to the axes. They allow you to estimate Gaussians that are oblique. So, for example, this is coded by the covariance matrix, and the way those for the C.
Okay.
You'll notice that from the start, just like in k-means, how well does this mixture generalize to new data that I'm going to see tomorrow, right? It's a feel-good kind of explanation. You read it and you say, this makes sense to me. Now I understand how to big K. In practice, you use it. It's going
Okay. All right, I watched the video.
to give you
I sort of understand
for
dimension. It's very, very similar to k-means, right? This idea of expectation maximization, right? It's like an iterative algorithm. First, assume. You first assume that there are a set of Gaussians that then you fit your to update your estimates based on the data. You have data 1. Goes P of xi given data I, P of data I. Which is equal to, you want to extract the marginal probability, which is P of xi times how do we get that? This the marginal probability. So it's Because, like, if that's the formula, then discrete case is like... And this is just a joint probability, so this is the joint probability of something is equal to right. Over what? Yeah, I'm having a hard time understanding the integral case. Like, I guess you're integrating over y. Why does my mouth hurt? Okay. Alright, we understand all of this. We went over expectation maximization. We understand marginal probabilities. Oh wait, I didn't finish my explanation of expectation maximization. They actually don't talk about like how is mu.
Move massively to the right because now
Oh, sigma squared is the same idea. Improve this. Yeah, this is the algo. Let me see what it wrote. Well, basically, you do a posterior update, and then you try to maximize or fit it better, right? And you repeat that. And it seems like Bayesian inference. This seems kind of similar to Bayesian inference. Yeah, I guess I don't see the difference. Dirichlet. Don't know what it looks like. Huh. Oh my god, conjugate priors? Oh, I freaking forgot that. Because we did this in the Thompson sampling. Mm. Alright, so that's the frequentist approach. I can't believe like I didn't learn this in my class. Woman in mathematics? Excuse me. So quite useful. think it's missing a gradient, right? Hmm. Huh? boy, this is kind of hard. How does Bayesian inference work? Sure. Bro.
Delight.
It's great to be here.
Wait, is that Thomas? We know Thomas, right? Thomas is, yeah, we know Thomas. Hmm? hope my machine learning course does that. This is pretty cool. Mode cutoff. I still don't get this derivation. This is really down a deep rabbit hole that is really overwhelming, and I don't think I need to understand unless I'm directly working with VAEs. I thought I could understand it, but I'm gonna need to spend more time on this, and I don't think I want to spend that much time. I can't even explain what elbow is, right? Like, I should be at least able to intuitively understand. Joint probability of this minus the Yeah, I need to get back to like working on code. I've been reading too much. It's like really bad. I spent a lot of time today reading on like learning from human demonstrations. I think it's good to read every day, but I spent way too much time reading today. We'll stop now. We're coding tomorrow, like at a fundamental level. We're gonna stream tomorrow morning. Wake up early. And get to work. Just work after, and ship. Because reading does not deliver any results.